Okay. Hello, everyone, and welcome to another exciting class of Math 211. We are in Chapter 20, testing statistical significance, which is all about coming into a situation and saying, oh, you're claiming some parameter has some value. The true value is this, proportion or mean or something. Well, I don't think that's right. I think it might be something different. So I'm going to test it, and I'm going to see whether or not I get a result that is statistically significant. What does that mean, a result that is statistically significant? It's so unlikely to have occurred under the assumptions coming in that I have to really change my assumptions. I have to say, sorry, I really don't think you're right, because if you were right, there's just no way I would have gotten this result. It's so unlikely to have occurred by chance that it's just, I'm sorry, I just have to reject it. Professor, I think we completed it. Thank you. Hopefully it'll say you're finished. That'll probably be a good indication that you're done.
No, that we completed this chapter.
Oh, the entire chapter? I thought we started it, but
Yeah.
we didn't finish.
No, yeah, last time we finished it because we had started it.
Yeah, we finished it.
Yeah, I didn't think we finished the whole thing, did we? Oh, we did. I remember all this stuff.
Mm-hmm. Yeah.
Well, sucks to be me. Okay, so 20 is done. What's 23 about? Probably confidence intervals. Almost we've done those already. Okay, margin of error. We have not done this, right? We have not done this.
No.
No, we're actually, to be honest, only 3 chapters to go with 4 class periods. We're actually doing really, really amazing. Faster than I've ever done it in previous semesters. So kudos to you for your success in that regard. I think it's pretty amazing. Anyways, chapter 23, margin of error. Give me 1 second, though. I'm going to stop sharing for just a minute. I feel that before we do margin of error, something else should have been done. So I'm wondering where those chapters are. So please just give me a couple minutes to find it. If you haven't done the survey, please finish it now while I do this. FYI, that spicy apple spicy thing is pretty good. 23. Very strange. Very strange. Okay. Hopefully it'll include it, because it seems like a little bit of a jump here, but it is what it is. Okay, so we're back. Where do you get the donuts? Just Dunkin' Donuts is one right off campus. Okay, margin of error. So we have an example. It says a Rasmussen survey found that 59% of American adults say that it is important for young people to go to summer camp. Now, the survey didn't ask all American adults, just 1,000. So it said the margin of sampling error is plus or minus 3 percentage points with a 95% level of confidence. So what exactly does that mean? Well, you have to recognize that when you take a survey, the results of your survey are not going to be exactly the true value unless amazing coincidence happens. Usually it's not going to be exactly the right percentage for all Americans. But if the sample is big enough, we assume that it's going to be pretty close. So the question is, well, how close? So if the results of the survey are 59% plus or minus 3 percentage points, we're basically saying, in this case, that we are 95% confident that the true value, whatever it might be, is between 56% and 62%. The 59% is the result of my survey, but my survey is only that. It's a survey. It's a small sample in the grand scheme of things. So there is some error involved. I can't tell you the exact value, but within 3 percentage points, I'm 95% confident that it's somewhere between those two numbers. If I want to be more confident, if I want to be 100% confident, would I make my margin of error smaller or bigger?
Smaller.
So let me answer your question. If your value is 59% and it's plus or minus 3, so you're saying it's somewhere between 56 and 62. Think of that like it's the size of your net that you're using to catch a butterfly or something. You have this net and you're trying to catch something. If you want to be more certain of catching it, do you want to use a bigger net or a smaller net?
A bigger one.
A bigger one. So the more confidence that you've caught it, the wider the interval is going to be. In fact, if you want to be 100% confident, just take it from negative infinity to infinity. If you're 100% confident, I promise you it's going to be somewhere between those two numbers, right? Mm-hmm. Whatever the true value is, it's somewhere between negative infinity and infinity, right? So the more confidence you have, the wider the net, the wider the confidence interval is going to be. Does that make sense?
Mm-hmm.
Everyone, make sense?
Yeah.
Okay. So for the summer camp survey, fill in the values that correspond to each symbol. So first we have the sample size. In that example, what was the sample size? How large was my sample?
1,000 people.
1,000. Now it said 59% of that sample say it's important for young people to go to summer camp. So the proportion of yeses in my sample was 59%, 0.59. Assuming that there's no rounding, how many yeses were there in my sample? $590, correct. Whatever 59% of 1,000 is, which is 590. In the context of this problem, what is P? Now, I'm not looking for a number here because if I knew P, I wouldn't need to take a sample to find it. Conceptually, what is P?
The number of people that go to summer camp or that say it's important to go to summer camp.
What do you mean the number? Like in the millions? What if 59% of all Americans felt it's important? We have something like what, 400 million Americans? So was P something like 230 million? Is that what P is? The number of people who say it's important? I'm not saying you're wrong, I'm just asking.
Is it the proportion of people?
Yes. It is the true but unknown proportion of all adults, probably American adults. I forget what that survey was. Was it Americans? Yeah, American adults. So it's a true proportion of American adults, whatever that number is, who say it's important to go to summer camp when you were a child. Now, did anyone here go to summer camp when they were a child? Is anyone here still a child?
At heart, yes.
That's what I'm talking about. I went to summer camp when I was a child. I was 7 years old. My parents shipped me away for 8 weeks across the country. It was awesome. I remember that. Well, I remember going. I don't really remember what happened in camp, but from what they tell me, I enjoyed it. Anyway, in the survey about summer camp, every number between 56% and 62% is a plausible value for the true unknown population proportion P. These collections of plausible values make up a 95% confidence interval. Why 95%? Because I am 95% confident that I caught it. If I was only 90% or 99% or any other percent, I would create a new interval. This is for 95%. And I can write it in two ways. I can either say it's from 56% to 62%, giving the left edge and the right edge. Or I can give the center 59% and say plus or minus 3%. 3% in this direction, 3% in that direction. And when you do it that way, the 3% is called the margin of error. How uncertain are you in either direction from the value that you got from the sample? The value that I got from the sample in this first example was 59%. 590 of the 1,000 said, yes, it's important. That's 59%. But recognizing that it's only a sample and that there's some error involved, I created, and we haven't learned yet how to create it, but I created this range of values that I claim give me 95% confidence. In this case, 3% left and 3% right. So where did that come from? So let's take a look. This sampling distribution was constructed with random samples of size of thousands, like our sample. But they were constructed, taken from a population where P was equal to 0.70. Now, if you look back at what we have here, P equal to 0.70 is not one of our plausible values based upon our sample. So let's see where they're going with this. They created one where P equals 0.7 is the center. Use this graph to discuss why 70% is not a plausible value based upon what we got from our sample. Why is it not a plausible value based upon what we got from our sample? Anyone?
Isn't it because it's not in that range of percentages? It's past it?
Well, yes, but what Alex just wrote to me is a little more precise. We got 590 as our value, correct? Where is 590 on this plot?
Not even there.
It's so far off the chart, to use Alex's words. It's so far off the chart that the likelihood of it occurring is negligible. In all of our samples, and we did lots and lots and lots of samples, this graph that we're looking at is just a sample after sample after sample using a simulation from a computer. And we got 700 lots of times. And we got numbers near 700 lots of times. And by the time we move over to 675 or 725, even those occurred every now and again. But 590 is so far off the charts that if P was truly 0.7, that is a completely implausible result. And yet it's the result that we got when we took an actual sample. It seems that 0.7 is not a reasonable value based upon our sample. Does that make sense? Yes, no? maybe
Yes.
so?
Yeah.
Okay. So what if I go ahead and instead make a new distribution, again, size 1,000, it's got to match ours. But this time I use 0.58 as my base true probability. In this case, is getting 590 an implausible result?
No.
No. So which means getting 590 when the true value is 58% is plausible. Getting 590 when the true value is 70% is implausible. So therefore, 0.58 should be one of those numbers in my confidence interval because it's a plausible result, right? Essentially what we're going to do, or what we could do in theory, is make lots of these graphs for different P's and pick the ones where 590 is a plausible result, throw away the ones where 590 is not a plausible result, and that interval that we have, that would be our confidence interval. Does that make sense?
Yes.
So to decide if a proportion is a plausible value for the unknown P, construct a sampling distribution for that P, and if your result, in our case 590, falls in the middle 95%, because remember, it's a 95% confidence interval, if your result falls within the middle 95%, then that P is a plausible value. Collect all those P's, and that becomes your confidence interval. Now, if you do it that way, while it sounds great in theory, you are checking lots and lots and lots and lots of P's to do this, and that takes a lot of time. And even if you did it that way and had all the time in the world, by the time you get down to the second, the third, the fourth, the fifth decimal place, how do you know exactly when to stop? So there has to be a more mathematical way of doing it, and in fact there is. But that more mathematical way is taught in Math 140, which I teach this semester. But it's not something that a sixth grader or a seventh grader or someone who's learning Common Core would have to know how to do. This idea is something that they would have to know how to do. In the California Common Core State Standards, margin of error is an Algebra 2 topic. That's high school. And it's developed in the context of these things called sampling distributions, which we've learned about. And what do they have to know? They have to take data from a sample survey to estimate a population mean or proportion. And they have to develop a margin of error through the use of simulation models for random sampling. That's exactly what we just did. We took two different simulations and we said, okay, this one's out and this one's in. And we didn't do all the rest, but in theory, that's what you can do. Does this make sense so far? Are there any questions on what we've done? Yes, no, maybe so?
No.
It's good, okay. So let's do this one. A study of 40 kleptomaniacs. Oh, my favorite type of friends. 40 kleptomaniacs found that 14 had onset of the behavior before age 11. What exactly would be the preliminary behavior for a kleptomaniac? Either you steal things or you don't. I don't know, whatever. Whatever they are, 14 of them had that kind of behavior before age 11. So in this example, what is my sample size?
40,
40. We looked at 40 people. How many yeses were there in my sample?
14,
14. So what proportion of yeses were there in my sample?
Would it be 35%?
35%. 35% of my sample. Now, what is P? The unknown population proportion. Again, I'm not looking for a number. You can't tell me the number because I don't know it. If I knew it, why would I take a sample? So when I say what is P, I'm asking in context, what is P?
the proportion of kleptomaniacs that had onset behavior before the age of 11.
Love it. The proportion of kleptomaniacs, because remember, all 40 were kleptomaniacs. So we're looking for the proportion of kleptomaniacs that had whatever behavior they're referring to before age 11. Now, 35% was the value that we got from our sample, which means that 35% is a plausible value for the true proportion. But it's not the only plausible value for the true proportion. Let's take a look on the next page at some different P's and see which of them are plausible and which ones are not plausible. So let's take a look. We have 6 of them right here. Each one, you'll notice, has the same sample size, 40. It's got to match ours. Here we have 0.1, 0.15, 0.2, 0.25, 0.3, 0.35, 0.4, 0.45, 0.5, 0.55. Look at all these. We got 12 of them. So what was our value again? It was 14 yeses and 35%. Okay. So let's take a look at the first one. Is 0.1 plausible based upon this sampling distribution?
No,
No, why not?
the 14 isn't even on the graph.
Yeah, 14 is off the graph, off the charts. So 14 is not plausible when P is 0.1. We never even got it in any of our simulations. And yet you got it? No, sorry, I don't believe it. 0.1 out. How about 0.15? Is that a plausible value?
No.
No, even though 14 happens, it is not within the middle 95%. So therefore, even though it occurred, it is not a plausible result. How about 0.2? Is that plausible?
No.
Well, let's take a look. The middle 15%. Would this constitute the middle 95? Not, I don't say 50. Would that constitute the middle 95%? Would 14 be in the middle 95% or not in the middle 95%? Like if I did this, how much is out? This is like 1%, maybe another 1% to 2%. So yeah, it seems like 14 is close, but not quite there. Would this be the middle 95%? We have 2% here and 2 plus a little bit. Yeah, so I don't think 14 is in the middle 95%. I'm going to throw this one out as well. How about 0.25? Is 14 plausible here?
Yes,
Yeah, now we're already in plausibility range. Or do the middle 95% here. 14 is inside of that. How about 0.3? Is 14 plausible?
yes,
Yeah, not only is in the middle 95%, it happened over 10% of the time. So certainly. How about 0.35? Is 14 plausible here?
yes,
Not just plausible, it happened more than anything else. So far, we have 0.2 is out and 0.25 is in. And how far can we get and still be plausible? Is 0.4 plausible?
yes,
0.45?
yes,
0.5?
yes,
0.55?
Yes.
Oh, let's take a look at 0.55. Where's 14? It's right there. Is that in the middle 95%?
No.
No, I don't think so. I think by the time we hit 0.55, we're out again. And certainly if we're at a 0.55, we're out for anything more. So I get, as my confidence interval looks like, about 0.25 to 0.5. That seems to be roughly my confidence interval for this particular situation. Now the center was 0.35. So it goes 0.1 this way. It's got to go 0.1 in each direction. So these are only approximate values. It's got to be the same in either direction. So maybe I'll go to 0.45. I'll say my confidence interval is 0.25 to 0.45, something like that. Does that make sense?
Yeah.
Everyone else, the silent majority, does that make sense?
Yes.
Yeah.
Okay. So the last Gallup poll before the 2012 presidential election, and this PowerPoint was made years, and I've been using this for years, this PowerPoint. So this is not recent. The last Gallup poll before 2012, that's 9 years ago, predicted that Obama would get 49% of the vote. The poll gave a margin of error of 2%. 2%. Which means the value would be anywhere between what two numbers?
48 and 50.
48 and 50 is one in either direction, which is a total of two.
47 and 51.
47, 51. Now we actually got 50.6% of the vote. Was that within the margin of error?
Yeah.
Yes. That's a pretty good sample if it had that much predictive power. Now the last Fox News poll before 2016 election had a 95% confidence interval for the percentage of votes that Trump would receive between 41.5% and 46.5%. What was the p-hat for that problem or for that poll? What was the actual result of the poll based upon those two numbers?
Would it be somewhere around 43?
Well, it would be somewhere around 43, but I'm looking for something a little more exact than that. I want the exact value. How do I take the edges, 41.5% and 46.5% and get the exact center? Oh, excellent. The exact center is 44%. Because if we go 2.5% up or 2.5% down, we get 41.5% on the downward side and 46.5% on the upward side. The easiest way of getting that, if you don't see it, is to just add the two numbers and divide by 2. The center is just their average. How do you find an average? You add them up and divide by how many you have. The same way we were doing it since second grade, right? Oh, I took 2 tests. What's my average? Well, you add them and divide by 2, correct? Yes?
Yes.
And then once you have it, how far is it from the edge? Well, then you just subtract them. 46.5 minus 44, 2.5%. Now we actually got 46.1% of the vote. Was that within the margin of error?
Yes.
Yes, it was. So we got some good poll takers out there. There's a very famous poll, by the way, a very famous poll in something like 100 years ago or so. I don't remember the details. I think it might have been Roosevelt's. I don't remember the details, but some magazine predicted that a certain contestant.
Oh,
would
I
win.
remember what you're like, that it was like the opposite, and then the one who won wasn't part of the polls, and it was
Well, yeah, it was something. I think his name was Dewey. I don't know why I have that name in my head. Huey, Dewey, Louie, and Fooey. I think his name was Dewey, and I think it was Roosevelt. And
yeah, I think it was, yeah.
and they took a poll, and Dewey, I believe, I'm going to say Dewey, even though I'm not 100% sure, but he was projected to win by a landslide. It just like wasn't even going to be close, and he ended up losing. And everyone was like, "What?" But the poll said he was going to win. What? What's going on here? And then it turned out that the poll was taken from readers of that particular magazine. And that particular magazine was a magazine for, and again, I don't remember the details, so I'm just going to guess here, but it was for Republicans. So the people who voted were all members who subscribed to that magazine, and the magazine had a very specific political slant. So the people who took the poll were very much aligned in that direction, and it must have been opposites to the guy who ended up winning. So this was an example historically of a very bad survey. It was not a simple random sample. It was not representative. It was really, really, really biased, and nobody noticed. Or if they did notice, nobody said anything. I don't know the details. I don't remember the details. But the point is that picking a good survey is a very, very important thing. In this particular example, this past slide, we have two very good surveys. So now, what's a formula for the margin of error? So this formula is not exact. When you learn Math 140 or a higher level stat class, you would learn a more exact formula. But for this one, we're going to give like a little approximation. And we're going to say that the margin of error is proportional to 1 over the square root of your sample size. So if your sample size is 1,000, as it was in that summer camp example, so let's go up, take out our calculator, and let's evaluate the margin of error when n is 1,000. I get 1 over the square root of 1,000. And when I do that, what do I get? What is 1 over the square root of 1,000? On your calculator, on your phone, in your head, what is 1 over the square root of 1,000? Yeah, 0.031622, which means it's about 3%. And if you go back up all the way to the top of this PowerPoint presentation, if you recall, it was 59% plus or minus 3%. So does that make sense? Again,
Yeah.
I'm not giving you the reason for it. I'm just giving you the results. Go ahead, everyone, please, if you have your calculator, and compute the margin of error for a sample size 40. What do we get there? .15811 is correct. That's about 16%. And if we went back up to that example, what did we actually, oh, we didn't actually get a margin of error for it. We just kind of, where is it? No, here it is. We didn't actually get a margin of error. Oh, we did. No, we did. Remember ours was, we guessed it to be approximately 0.25 to 0.45, right?
Yeah.
Okay, so we got a margin of error of 10%. So ballpark, we were up by 5%. We were eyeballing it. It wasn't going to be perfect, but it was certainly in the right ballpark. Okay, now, suppose I want a margin of error of 4%. So now we're working backwards. Suppose I want a margin of error of 4%. How do I determine the sample size necessary for that? This is for everyone. How do I determine the sample size necessary if I know the margin of error in advance? Anyone?
You square it?
Huh?
Don't you square it?
You can square it. That's certainly part of it. Go ahead and do that.
Then I got 0.0016.
0.0016 for your sample size doesn't seem reasonable, does it?
No,
It's a pretty small sample size, isn't it?
yeah.
Let's see, you said 1,000 was 3%.
No, let's not do it. Let's not do it by not do it that way. Let's do it by math.
Okay.
Okay, so my goal
But I
here.
did get it. Squaring it.
Okay, well, mathematically, how would I rearrange this formula to get n by itself?
You multiply by the reciprocal. Wait, what up? Because I kind of did it, but then I didn't get it right. Because you would have to multiply by 1.
So, Sabina, you wrote 1 over the square root of n equals 0.40. First, remember, 4% is not 0.40. 4% is 0.04. Right? Now, how do I get n?
Wouldn't you multiply both sides by radical n, divide by e, and then square both sides?
Okay, so the two things you went there. If we multiply both sides by radical n, going to this side, I get root n times e is equal to 1. Squaring both sides will help too. If I then divide by e, I get root n equals 1 over e. And then if I square both sides, I get n is equal to 1 over e squared. So let's go ahead and plug in a 4% margin of error and do that. So what do I get? 1 over 0.04 squared is how much?
625. 1 over 620.
Not 1 over 625. Remember, e is small.
Oh, yeah. So,
So
yeah,
1
625.
over n. So if I want a margin of error of 4%, I would need a sample size of approximately 625. I say approximately because even though this formula gave me exactly 625, this formula is in and of itself an approximation. So if I was an actual statistician, I would want to use a more accurate formula than this hand wavy one. Does that make sense?
Yeah.
Okay. Now, so if you want to be highly confident of estimating a probability to within an error of E, n equals 1 over E squared runs in your simulation, that's the one that we just did. Right? We rearranged the math and we got n equals, I already erased it, but we got n equals 1 over E squared. It's just giving me the final value. So, interpreting a confidence level. What do we mean by 95%? 95% confidence. What we mean is if we took random samples over and over and over and over again, 95 of them will capture the true value. The way we really think about it when we say we're 95% confidence is there's a 95% chance that we caught the true value. But rigorously, it's the first version. It's 95% of our confidence intervals will capture it, and 5% of them will not. So if I make lots and lots of confidence intervals, 95% will capture the true value, 5% of them will not capture the true value. I don't want to do this one. It's a class activity and it's got to be done in person. So we're just going to skip it. Okay, a Harris poll conducted online with 2016 adult Americans found that 21% said that they had some sort of tattoo. So what's my sample size here?
2016.
2016. How many, what proportion of them said yes in this problem? What's my proportion?
21%.
21%. How many does that, I mean, assuming it's an accurate value, how many is that?
Around 424.
Yeah, 420, well, 423 is actually a little bit closer. So while it could really be either one, we'll say 423. What is P? The true unknown thing that we're looking for. What is P in this example? What is P?
Would it be
Proportion,
Sorry?
the proportion of adult Americans that said they had a tattoo.
The proportion of adult Americans that said they had a tattoo, not the actual percent that have a tattoo, just the proportion who said they had a tattoo, which is probably similar. Now, what must be true before you can compute the margin of error? That's a weird question. What must be true before you can compute the margin of error? Well, our formula says that we need to know the sample size, which we do, but it's not really what must be true. Knowing the sample size doesn't have to be true. It's just, if you know the sample size, you can do it. I would probably say that it has to be a good sample with no bias. What must be true? It's got to be a good sample. It has to be representative of all adult Americans. Otherwise, the whole sample is nonsense. I would never ask a question like that in the test. I hate those types of questions. But my guess is that's what they're asking for. Now, what is the margin of error? Or at least approximately so? What is the margin of error? Anyone? The margin of error is 0.022, no, not 5%. Regina was right, it's around 2.2%. Elizabeth, how do you get 5%?
I used the formula, but I might have done it wrong.
1 over the square root of 2016?
No, I used 423. That's probably why.
Yes, 423 is the number of yeses, but it wasn't our sample size. Right?
Yeah, right.
Okay, so we get a 2.2% margin of error approximately. So we are 95% confident that if every adult American could have been asked, the percentage who would have said that they had a tattoo would fall someplace in the interval about 19% to 23%, rounding to just the whole number and not worrying about the decimal. Does that make sense? Thank you, Alex. You too. Does that make sense, guys?
Yeah, yeah, it does.
Okay. Now, proportions are not the only type of confidence interval we can make. Confidence intervals can be constructed for parameters other than the proportion of yeses. And the interpretation is the same. I mean, whether I do it for proportions or for means or for ratios of means or ratios of proportions or standard deviations or this or that or anything that I want, when we say we have a 95% confidence interval, we mean that if we kept taking samples, 95% of our intervals will capture the true value and 5% will not. So here's an example, not dealing with proportions. The temperature of a random sample of 65 men was measured and the mean was 98.1 degrees Fahrenheit. A 95% confidence interval for the mean temperature of all men was constructed from the data, and we got 97.9, 0.2 down, to 98.3, 0.2 up. For a sample of 65 women, the confidence interval was 98.2 to 98.6. So two things. One, the temperature for women was a little bit higher, although there is some overlap. And the spread was a little bit bigger as well. So is 98.6, actually the spread is not bigger. It's still 0.4, 0.2 in both directions. It's just centered a little bit higher. So is 98.6 degrees a plausible value for the mean temperature of all men? Would 98.6 be plausible for the mean temperature of all men? What do you say based upon the data? Is 98.6 plausible?
Yes.
What's the confidence interval for men from where to where?
98.2 to
For men, not for
Yeah.
women, for men.
Oh, so then
97.9 to 98.3.
97.9 to 98.3.
And so is 98.6 plausible?
No.
No. What about for women?
It is.
Well, it's on the border of being plausible and not, so, right?
Mm-hmm.
Yeah.
So yes or no, it's on the border. What was the average temperature of the women in the sample?
$98.4.
98.4. Good. Is this convincing evidence that women are hotter than men? And when I say hotter than men, I do mean temperature-wise.
Yeah,
Why?
because they maintain a consistent temperature.
Well, I mean, their spread is just as big as the spread for men.
Is it because the men's average was 98.1, which would mean that women are hotter?
Well, it means on the average they were hotter, but remember, these are just samples, right? These aren't all men or all women, right? These are just samples. And we're trying to take from our sample and extrapolate some information about the entire population. What do you notice about the interval for men and the interval for women when they are lined up next to each other, or when we look at them both at the same time? They overlap. There are some numbers that appear in both, correct?
Yeah.
Every number in the interval is plausible, which means it could be that they're both, for example, 98.25, right? 98.25 is plausible for both, right?
Yeah.
Anytime there is some overlap, you cannot conclude that they are different. Does that make sense?
Yeah.
So in this case, because there's overlap, we cannot conclude that women are temperature-wise hotter than men. And look at that. We finished number 23. That's crazy. So we are done with the chapter, which was amazing. Just really a great job. I just rechecked the survey. 19 of 35 have completed it. So there's 34 of you here. So we're going to end the 7 minutes early right now. And please, 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 the more people who do it, even if you say bad things, I don't even really care. But the more people who do it, I'm going to put it in the chat again. It looks better on me as a professor when more people do it. So I'm asking, please, everyone, to just do the survey. I mean, be honest, it does not take more than what, 5 minutes? Something like that. I'm gonna let you off 5 minutes, 6 minutes now. www.csun.edu/SEF. Please, please, please. I am asking, I'm gonna stop recording, but I'm gonna ask